compute WS. It's not complete, sorry. I'm not repeating this step by step because I am pretty sure that you did it already in other subjects. But please, if you keep in mind that I may ask you how to derive WS, it could be a question at the exam. Everything is explained here. It's really self-explaining, and so you have to have a look at it. Even if you already studied it, keep in mind that I may ask it, and therefore please have a look. Because it's nice. I think it is a nice proof. It's nice because it proves, it relies on concepts of equilibrium between the gravity forces and the resistance forces that oppose to sedimentation. Resistance forces by water, by the fluid. I think it is nice. I like it. And this is why sometimes I take the opportunity to teach it, but I don't think it is really needed because I'm sure that you did it already. Okay, and that's it. So, I'm sorry I covered the blackboard, but if you need that I raise the screen, just let me know. And I think that now you have everything you need to design the sand trap. What is the order of magnitude for the length of the sand trap? It can be very long. I know that I saw sand traps long, 30 meters long. So it may be between 15 meters to 30 meters. And usually these structures, the length, the total length of the structure is something that can be between 15 meters and 40 meters. I'm talking about fixed barrages. A barrage with regulation may be much longer. Okay, now if we look at the web page, and let me decrease the font size, there are some more information that are delivered here. So basically, after the description of the barrage, estimation of the design flow, and sorry if I scroll down very quickly because we discussed yesterday already. And then there is a description of the elements, the determination of the elevation of spillways, and we described everything here. And then there is the formulas for determining the elevation of the spillways, design of gravel and sand traps, and we discussed everything here. And there are a couple of paragraphs related to the design of the head tank. They are very easy to understand, and design of side structures. And please read by yourself the design of the head tank. There is a formula here, which is empirical, not really empirical, but it's, let's treat it as an empirical formula. And in order to determine the submergence, the minimum submergence for the sealing of the pipe, please learn it. But I leave this to you to read because it's very descriptive. And for the design of the side structures, same thing. There are some descriptive issues, and then there are a couple of things that I wanted to discuss with you, which are two final details. One is the verification of the structure of the whole structure against piping. Do you know what is piping? It's water flow under a structure. So we build a transversal structure over a river, we accumulate water upstream, water makes pressure not only against the structure but also over the riverbed. And for effect of the increased pressure, water may infiltrate in the riverbed and bypass the structure from the riverbed, along the riverbed, beneath the structure. And then water emerges back downstream. This is something that we need to absolutely avoid. The reason is that if you have water flow under a structure, the flow produces erosion, and therefore the small channels along which water flows become larger and larger. At the end of the story, piping causes the collapse of the structure. So this is absolutely to be avoided. No matter if the structure is a levee, which is a longitudinal structure, or it's a dam, even worse. For dams, absolutely we need to avoid, but also for these barrages we need to avoid piping. Piping in Italian is called siforamento. It's absolutely to avoid. And there are technical procedures for estimating the risk of piping. There is an empirical rule, which is the Lane or Lane rule, written L-A-N-E, which you may already have studied in geotechnical engineering, probably. It's an empirical rule. Basically, there is a safety factor F, which is prescribed by the literature, depending on the type of soil, that has not to be exceeded, and this safety factor is given by a ratio. The ratio is water level against the structure upstream. At the denominator, we have the sum of the 1/3 of the horizontal length of the flow plus the vertical length of the flow. So, give me a piece of blackboard. It's still there. So you have your barrage, which if you look at a transversal section is something like this, and then there is some foundation, and then there is the riverbed. Okay, perfect. And then you have upstream a water level, a max water level. The max water level is, the water flow of the structure is something like this, and you have a max water level which is H. This is what gives the pressure. If water wants to bypass the structure beneath of it, water has to travel for an horizontal distance, which is called LH, which is this one. LH, and a vertical distance, which is this one, LV, which is repeated twice, LV. So, you compute the sum of LV plus 1/3 of LH, and this is the denominator of this relationship. F is again described by the literature. You cannot exceed it. This is a rule of thumb, it's an empirical rule, which can be used for the preliminary design. For the final design, you need to stick on something more elaborated. If it's not verified, what we need is to build a sheet pipe below the foundation. You build a sheet pipe. Sheet pile, you know what is? Sheet pile means a kind of vertical wall that goes beneath the structure for a predetermined depth. And the sheet pile can be made by concrete or by metal. And what is the purpose of the sheet pile? To increase the vertical path of water. Sheet pile, diaframma in Italian. finally, one last thing. Why we shape the downstream part of the main spillway in this way? Because we want to accompany the river flow downstream. We don't want the river flow jumping out. If the structure is really small, we can allow for the flow jumping downstream. But if the flow is important, which means that the structure is important, we need to accompany the flow. We don't want jumps, because jumps are dangerous for the structure and for the riverbed. So we accompany it, and in order to avoid jumps, this has been shaped in a particular way. And there is an analytical relationship, which is called Krieger profile. Krieger, written this way. Which is suggested. You don't have to learn it. And you can find the Krieger profile. There is a link on my web pages. And I don't find it here. If you click here, basically, this is in French, but the profile is very well understandable. Here, you see Krieger. It's written, I think it is misspelled here. And there is everything that you need to understand. But in any case, you don't need to study it. You just need to know that there exists an analytical relationship to design this profile. That's it. Okay, now, I rushed a little bit, but I can tell you I'm quite confident that you don't have any problem in studying this. Because the concepts are a bit difficult to explain, especially by speaking in English. For me, it's a bit, I need to be extremely clear, and so it's not very easy to teach. But I'm sure that when you read, everything becomes clear. And in any case, if you have any question, next Monday is a good opportunity. And in the question and answer, there is one question that I would like to ask you. And this may be something that we discuss on Monday, which is a proactive push in order to make you understanding what you're doing and try to understand really how these structures work. And let me go back to the sketch. This is a kind of very difficult question that I could ask at the exam. You know that I mentioned to you that during the exam sometimes if I see that you are very well prepared in order to resolve my doubt on whether or not to give you the laude, I may ask some tough questions. This one that I'm now asking you, it's very tough. But still I think it is interesting and to give you an example. So, when I talked about the width of the environmental flow spillway, I said it's about ½ meter, okay? Keep in mind that we can't use here any gate. By law, we are not allowed, unless there is an exception that is made by the local administration, we are not allowed to put any gate here. We are allowed to put gates on the diversion spillway, not here. And so my first question is why, in your opinion, we are not allowed to put a gate there? This is simple. But don't reply now. On Monday we may discuss on it. So given that we are not allowed to put a gate here, our clients usually ask us to make this weir to reduce the width, like 20 centimeters. So my question is why? And usually we can't do this because the fishermen, they want that the weir is large enough to allow fishes, even big fishes, to pass. Because usually, this is something that I didn't say so aquifer, there is a fish ramp that is called the downstream, and the environmental flow spillway is the door that allows fishes to climb up the structure by swimming along the fish ramp downstream. They pass through the environmental flow spillway, and therefore the fisherman says, and they ask for the local laws to fix a minimum width of 50 centimeters. But this is not my question. My question is, why our customers, which are of course motivated to divert the highest possible amount of water, why they ask us to reduce the width of this environmental flow spillway, given that they are forced in any case to release the environmental flow. They need to release it. So the reason why they are asking to reduce the width is not to reduce the environmental flow, because it is required by law. So the environmental flow doesn't change. They are not allowed to put a gate, and therefore they say, please make it less wide. Why? You don't have to reply now. I would be very surprised if you replied now. Ideally, they would like it to be like 10 centimeters, but then we say, no, sorry, we cannot. Half a meter is our suggestion, but they want to reduce its width. Okay, now, what I'm proposing, actually, I have about half an hour. So, as I said to you yesterday, today I also would like to look at the exercise that we have to develop together, and I asked you to bring your PC. So, I think, let me try to indeed go back to the exercise, because if you remember, we didn't finish it. And therefore, I would like to look at the code and finish the discussion of the code. If for some reason you need to leave now, you can do it whenever you want, no problem at all, okay? And one question, I saw some people arriving late, and did you subscribe to the field trip already? Yeah, okay, perfect. Okay, let me go back to the exercise then. I'm not sure whether, give me a couple of minutes, I'm not sure whether I still have it in my desktop. Yeah, it seems that I have it, but I don't. No, sorry, I need to. Yeah. I need to download it again. Okay, this is our code, and you remember that we introduced it as a function, and we got here. We got here. Let me see. So, you remember that we estimated through the code the contribution to surface runoff, and we split it in two parts according to the weight alpha. And then we got to the stage where we had to route the contribution through the sequence of 3 reservoirs for the slow flow and the single reservoir for the quick flow. So, this is the routing, sorry, for the slow flow. I inverted slow with quick in my previous sentence. So 3 reservoirs for the quick flow and 1 reservoir for the slow flow. So this is the slow flow component, and this is the formulas that allows me to apply the linear reservoir. Let me recover a piece of blackboard. Okay, let me see if, oh yeah, it's still there. Okay, so for the single linear reservoir, we have here a flow entering into it, and then we have the reservoir with the bottom discharge, and the reservoir has a storage which is called W slow. W slow, which depends on time. Here we don't see the dependence on time because we are inside a cycle, and the cycle is repeated each time step. So basically, W slow and Q slow are updated at each cycle, therefore obtaining an update at each time step. So you don't see the dependence of time on time for that reason, but this depends on time. And here we have our inflow, which is U slow. U slow, which is equal to, I'm copying from there, 1 minus alpha, which multiplies E R I, and here I is the step of the cycle which highlights the dependence on time. So this is the contribution to the surface runoff. I multiply it by the weight 1 minus alpha, and then I get the U slow entering into the reservoir, and then I have the Q slow which goes out, which is equal to now, what is the question? The question is to try to understand how these relationships are obtained. And I already anticipated to you that K is K's law, in this case here. K's law has the dimension of 1 over time. Now, my question for you now is, let's try to understand how these relationships work. And I suggest, this is merely an application of the linear reservoir. I suggest, given that, because I wanted to derive these together with you, but it takes some time, I suggest that we skip this for now. Let's take it for granted. If we look at here, there are two analytical relationships that allows us to compute at each time step the outflow from the linear reservoir and the storage. What we don't understand is how they are computed, because we are used in our application of the linear reservoir, we did something different. Let's skip this question for now. We may discuss in half an hour if we have time. My first priority today is to get to the end of the code. If we have time, we can discuss it, otherwise on Monday, okay? And it can be a question that we resolve on Monday. Now we go to the series of the 3 reservoirs for the quick flow component. So basically you see that there is a cycle which is nested into the main cycle of our simulation. A cycle that is extended over 3 reservoirs. J is varying from 1 to 3. And within this cycle, we use the same relationship that I used above, whose understanding of the meaning we skipped, in order to compute the W quick and the Q quick, the outflow from each of the reservoir. There is this instruction added here because we substitute the outflow from each reservoir with the inflow of the next one. So basically here we update U quick for the next cycle. The next cycle is the next reservoir. We equate U quick contribution to the next reservoir to the outflow from the current reservoir. But it is basically a repetition for 3 times of the 2 relationships that we applied above. Okay, now let's move forward. And then we get to the total flow. The total flow is given by Q slow, slow component, plus quick component, times the conversion factor. Okay. The conversion factor, remember, is needed because we are using storage in millimeters times in hours, and we are referring to unit area of the catchment. The conversion factor allows me to express the result in cubic meters per second. The computation of the conversion factor is on the top of the code. I go to the top for just 1 second. Here it is. Conversion factor is equal to 1 divided by 1000 because we want to pass from millimeters to meters. No, it's not. Okay, it's here. Times time step in order to pass from hours to seconds times area of the catchment. Okay, let's go back. Let's go down. And now here, at the end of the code, there is, unfortunately, I cannot scroll down, but there is simply a drawing of the plot. If we want a plot, meaning that if after running this function, we want a plot, here there is a possibility to draw it. And if you don't want a plot, you have to comment out these instructions here. And the comment, you see the comment you know already. You have to put a dash sign at the beginning of the line. And the plot is something that you already know. Basically, there is here there is the opportunity to start the plot from different points with respect to SK. SK is the initial timing of our simulation, which was fixed above at the beginning of the top. And then we can plot Qt. What is Qt is what we obtained above. It's a simulated river flow through a line. And also I put here limits for y. And the limits for y, note this. Why do I have to specify a limits for the y-axis? The problem is that I have to draw 2 lines. The first line is the simulated flow, and then I want to draw the observed flow over it. But if you plot 2 lines, then you have to adapt the scale of the y-axis to the range of the most varying line. And you don't know if the range of variability of the simulated flow is lower or higher than the range of variability of the observed flow. So you need to specify the range of the y-axis by looking at the range of variability of the most variable line that you want to plot. So, what is the solution? The solution is to fix the limit for the y axis, ipslim is the argument of the function plot, which allows you to specify the range for the y-axis. So y-lim is 0, because for sure we are dealing with positive variables, so it's fine if we set 0 as lower level for y, but the upper value, it's decided with this instruction, the maximum of what? The maximum between q, t, and the maximum of qos. So we first get the maximum of the observed flow, the maximum of the simulated flow into a vector, and then we compute the maximum of this resulting vector. So it's the maximum of the maximum. So maximum of observed, maximum of simulated, maximum of these two maxima. And therefore, I fix the range of y in a convenient way. Okay. And then there is the width of the line that is set to 2, so twice. And then I put over it the observed flow through the instruction, through the function lines. Okay, that's it. Now, if you want, you can print on the screen the parameter values, and you may say, why do I need to print on the screen the parameters? Because the parameters, I decided them at the beginning in order to run this code. Please remember it. You need to fix, to give as argument of this function that we are writing, this function imod, we need to give the parameters. Okay? If we look at the first line of our function, you see imod is a function of the argument parameter. So this is something that you have to specify, to give to the program, parameters. Okay, so you may say, so what's the reason why I should print out the parameters on the screen? I know that. Okay, my reply is, wait a moment, I'll explain to you why there is here this instruction and why it's commented out in this case. And then there is the final instruction, which is extremely important. We have to tell the function what we want to be returned as a result of the function. Clearly, a function gives to you a result. In R, when you apply a function, you get a result. We have to tell this function what we want to back, what we want to get back. So, there are two possibilities here. The first possibility is to return the simulated flow. If you want to get back the simulated flow, you have to uncomment this line and comment the following one. But there is a second option here, which is uncommented now. And the second option is to give back the sum of squares. Look at here. Sum of the difference between Qt simulated flow minus Qos observed flow squared. This is the sum of squares. Because when you run a model, you may want to get back the simulated flow, but you may want to get back the sum of squares. Because we already discussed that for calibrating the model parameters, you may want to refer to an objective function. Okay. And then we close the curly bracket of the function here. Look, we closed above there. I forgot to mention to you before. The curly bracket of the fourth cycle. And we close here the curly bracket of the function. We are done. So, what can we do with this function? With this function, we can run imod. We need need to specify the parameter values. We need to have the variables defined in the R environment. And the variables are E, evapotranspiration, P, precipitation, QOS, observed flow. And then we can run the model and we can get back either the simulated flow or the sum of squares. This function may allow us to perform a trial and error calibration procedure. And this is the key message that I want to deliver to you. Basically, you can try different parameter values in order to see what is the combination of parameters that makes you more happy in terms of simulated river flow, and you look at the graph in this case, you look at the plot, or in terms of the sum of squares. That's it. But the exercise asks you to perform an automatic calibration. I think it is explicitly requested. I don't remember. But in any case, I want to give you the tools for performing an automatic calibration. Indeed, there are several options in R that allow you to find the optimum of a function, which means